Most people, including myself, think integration is more difficult than differentiation. To me, differentiation is like walking forward and integration is like stumbling backwards. To avoid falling down, let's take a quick look at some strategies that will make integration easier for you. In the classroom, the question I'm asked most often is, how do I start this problem? What do I do? I don't know what to do. Typically, once I get a student started in the right direction, they take off and no longer need my help. So let's answer that question first. How should you start an integration problem? Well, the first thing you should say to yourself is, did my instructor give me an easy problem? Well, it is true that teachers like to make students' lives very stressful. They can occasionally be nice. An easy integral problem is one that has an integrand that fits one of the many rules of integration. So keep that rule sheet on your desk and with you at all times. Well, we figured out it wasn't a rule. So what do we do now? Well, number two is, will my previous algebra instructor be mad at me for not knowing how to start this problem? You learned arithmetic and algebra hopefully not too long ago. If you did not find a rule of integration, take a look to see if there's any algebra that could be changed or simplified. Well, now that we've made your algebra teacher happy, let's see if we can make your trig teacher happy. Will my previous trigonometry instructor be mad at me for not knowing how to start this problem? Well, let's take a look at our trig identity sheet. You do have it sitting on your desk, I hope, because it should be right next to your calculus rule sheet. Oh, and by the way, have you looked for a rule to make sure that there's no rule for this particular problem? Okay, it's not an easy problem, and my algebra instructor let me down, and so did my trig instructor, so I guess we're stuck with number 4. Is there a function that consists of more than one simple function? These are called composite functions. When you see one function inside of another, use substitution is going to be the way to go. Now let's take a look at some integrals and determine just how we should start them. At this point, I'd really like to take a break. I need to go get some coffee. So what I'd like you to do is pause your computer and try these 6 problems on your own. For each integral, determine which of the 4 techniques you might use to start the problem. If you don't have your calculus rule sheet and your trig rule sheet, you better go get them because you're going to need them. Now please, right now, pause this video and try these 6 problems. Did you really pause the video? Well, it's okay if you didn't. Here's our first problem, 1 over x squared. Now that little 2 wasn't there, that would be the integral of 1 over x, and there is a rule for that. Go look it up if you can't remember it. But it's not 1 over x, it's 1 over x squared. So that needs some algebra. We change that fraction into x to the negative 2 power from the algebra days, and we then can use the power rule. Now the next one, which looks very, very similar, number 2 is 1 over x squared plus 4. So throwing in that little 4 makes a big difference. And we can go to the rule sheet and we can find the arctan rule, one of the rules which you probably did not use a lot in Calculus 1. Going to number 3, which is also a fractional problem. So far we got 3 in a row. And we see a linear function, 3x plus 7, hiding underneath that fraction bar, which is a reciprocal function. So we've got 2 functions, a linear function inside of a reciprocal function, and we let u be 3x plus 7, and then du would be 3dx, and we're on our way to a u sub problem. Number 4 has also got a fraction, 1 over sine squared. Now, unfortunately, there's not a rule for 1 over sine squared. In fact, there's not a rule for 1 over sine. So we go look into our trig sheet, and we very quickly find that 1 over sine is the same as cosecant, which then implies that 1 over sine squared is the same as cosecant squared. And guess what? That's a rule you may never have used. So we have to keep on digging to find an answer to the question. Number 5, x plus 8 squared. Well, I'll tell you, my algebra teacher would get pretty mad at me if I didn't FOIL that out and get x squared plus 16x plus 64. So that's what I would do, and then use some simple rules of calculus to get the answer. On the other hand, if my algebra teacher told me to multiply out x plus 8 to the 30th power, I'm not sure I would listen to that algebra teacher. So rather than doing that, this would be a u sub, where u would be the inside x plus 8, and du would be 1 dx, and you'd be on your way to solving the problem. Well, I think I need another break. Here's 4 problems that I'd like you to try. So give them a shot. Take a piece of paper out and try each one. One of them is going to be pretty simple. You probably can guess what it is. and the other three are either very difficult, well, somewhat difficult, and maybe even one is impossible. So I'd like you to try this on your own paper. Pause the screen, don't peek, and after you're done, take a look at your answers and double check them. Make sure maybe if you take the derivative, you have the correct answer. And if not, try it again, but don't wait too long, and you can unpause the screen and I'll show you what's going on. So let's take a look at how many you solved correctly. If you saw that problem 1 was just a basic integration rule, awesome. You're absolutely correct. Problem 2, on the other hand, contains a composite function made up of the linear function 3x. 3x is inside the exponential function e to the x. We need to somehow change the composite function so that we can integrate it. The process we use is differentiation, which sounds a little strange since we're integrating this function. We're going to go forwards and then go backwards. Sounds like our car is stuck in the mud. Let's start by letting u equal 3x. Differentiating both sides gives us du dx is equal to 3, and a quick multiplication gives us du is equal to 3 dx. To create the perfect integral for this problem, there must be a 3 in the integral. So let's just put it inside there. But we really need to be careful here. The integral of e to the 3x dx is not the same as the integral of e to the 3x times 3 dx. How can we maintain the equality of the integral? I know. Let's make this problem even longer. We know that multiplying by 1 doesn't change anything. So how about we balance the equation by putting 1/3 in the problem as well? We put the 1/3 outside, but remember we can do that because constants can move in and out of an integral at will. But never, ever, ever put a variable into an integral. It changes the problem. Now that we have built the perfect integral, we replace the variable x with the variable u. The result is 1/3 e to the u du. Our composite function is hiding inside that u function, so we can use the rule. Applying the rule, we get 1/3 e to the u, but don't forget, we got to bring back x. Remember, we are looking for the integral of e to the 3x. So the final answer is 1/3 e to the 3x plus c. To check your answer, apply the chain rule for differentiation to your answer, and we go right back to e to the 3x. The key to understanding u substitution is to first notice that you have a composite function. Second, the derivative of one of the parts of the composite function must also be contained in the integral. If a number is missing, we can put it into the integral as long as we balance it with the reciprocal of that number. Now let's take a look at problem 3. Looks pretty intimidating, but it is actually quite easy. We see a composite function made up of the sine of x and e to the x, where sine of x is inside e to the x. Right next to that composite function, we see cosine of x, which conveniently is the derivative of sine of x. Problem 3 needs nothing else. Let u equal sine of x, du is cosine of x dx. Switch variables and we have the same integral as we had in problem 2. Of course, our u is considerably different. The result is e to the u, and back subbing, we have an answer of e to the sine of x plus c. Problem 4, on the other hand, is really big trouble. We have the same composite function, e to the sine of x, but where's the derivative of sine of x? Not there, is it? And we can't put it there. It's a function. It's got the variable x in it. This problem is impossible to solve by anyone. Not me, not you, not anyone. So how should you start that integral problem? Number 1, is there a basic integration rule? 2, no basic rule? How about algebra? 3, how about a trig identity? 4, do you have a composite function? Use u substitution. Over half this course is related to integration, which is why we start with a review of integration from Calculus 1. Please spend some time sharpening your integration skills. It will be time well spent.